Hi, so today we will discuss about the canonical products and a very important result due to Weierstrass, the Weierstrass product theorem. So that is what we will do. We begin with a short lemma. So we assume that fz is an entire function and which is non-zero. That means it has no zeros. So that happens only when fz has the form exponential power gz, where gz is an entire function. You know that this is a property enjoyed by the exponential function. It is entire and non-zero. So this tells you that any entire function with this property will be of such kind, some exponential. So this is easy to prove. So if something is of this form, you know that it is definitely entire and non-zero. Now you look at the converse. Suppose fz is entire and non-zero. So then what happens that f dash z by fz is also entire, because fz is non-zero. So this is an entire function. So there exists a function g1z such that g1 dash z equal to f dash z by fz. I mean, every entire function has a primitive. That is easy. So now what happens? You take f tilde z to be fz into e raised to minus g1 z. Now it is easy to prove that this f tilde has derivative 0, therefore f tilde z is a constant. That means fz into e raised to minus g1 z is a constant and that is non-zero. That means fz is equal to c1 e raised to g1 z. Now you put c1 equal to e raised to c1 is a positive non-zero constant, so you can put it to be some exponential c. So that will give you fz equal to e raised to gz, where gz is this. So that's a simple proof. Now let us see some consequence of this. So suppose fz is entire and has a 0 at origin of order m. Then what happens? You know that you can factorize it. So it is the form fz equal to z raised to m into f1 z, where f1 z is entire and not equal to 0 at the origin. If f has no other zeros, then what happens? f1 is an entire function which is non-zero. Therefore, by previous result, f1 z you can write it as e raised to g1 z. So what happened? fz is equal to, from this, fz equal to z raised to m into e raised to g1 z. So this is the form of an entire function which has only one zero at the origin of order m. Now suppose 0 is a 0 of origin is a 0 of order m, and a1, a2, an etc. are the other zeros. Only suppose there are only finitely many zeros repeated as per their multiplicity. Then what happens? You have the factorization again, z raised to m into z minus a1 etc. z minus an into f1 z, where f1 has no zeros. It is entire and no zeros. So f1 you can write it as exponential g1 kind, gz kind thing. Now what is the final form? fz you are able to write z raised to m e raised to gz into this product. I mean, this product, what I do some manipulation and obtain like this product n equal to 1 to n 1 minus z by a. That is easy. I mean, I'm just taking the common term outside and writing this. So this is the form you get. If fz is an entire function with 0 at origin of order m and all other zeros are ans, finitely many, then fz has this form. So that means it characterizes all such functions. They look like this explicitly. It has a form like this. Now the question is, do we have a similar representation if fz has infinitely many zeros? That's the question. In fact, this question came from a pioneer work by Euler. In fact, his work, he considered this function, sin pi z by pi z. You notice that sin pi z by pi z has zeros plus or minus 1, plus or minus 2, etc. And limit z tends to 0, sin pi z by pi z is 1. And therefore, what we expect? What are the zeros? Zeros are exactly the plus or minus integers. It means all the integers, non-zero integers. Now, looking at this, you have product n equal to 1 to infinity, 1 minus z by an should come. So instead of an, you will have plus or minus 1 here. So plus or minus 1 means 1 minus z by 1 and 1 minus z by minus 1. You take them together, then what happens? It is 1 minus z square by n square. So Euler conjectured that this series product representation is true. So without bothering to the convergence issues. So after proving all the results, all the Weierstrass rigorous estimates, everything, finally we will end up with this formula, which Euler predicted in 1735. So this is the main result, Weierstrass product theorem. So it tells you that if a sequence, infinite sequence, which goes to zero, which goes to infinity is given, then you are able to find an entire function with zeros exactly at the points a n. That's what we can prove that that existence. More generally, every entire function will look like, with zeros at a n and a zero at origin of order m will look like exactly like this. This is the expression for that. You can see that you have a term set raised to m that is understandable, because origin is a zero of order m. You have a quantity like this, exponential power gz, which is again we have seen that, and there's a product like this where ans are the zeros, other zeros, non-zero zeros, and an additional term come into picture. This is something additional. In fact, I will tell you how it comes. Now this product is taken overall and not equal to 0. So now this is a result which we are going to prove. Now first of all, you consider these infinite products. See, if this product converges, then it is easy to prove this. So this converges absolutely when exactly when, so we have seen that this converges. So one second. So we have seen that so we know that this product converges exactly when this summation converges absolutely. So this is the term here. So the absolute value of this. So this series converges absolutely if and only if the product converges absolutely. So now the question is, when does this series converges absolutely? So let us look at here. So this happens exactly when this series converges. Because z is a fixed term, so you can take it out. Absolute value z, you can take it out. So also this convergence is uniform in every closed disk mod z less than or equal to r. That is true. And we are given that a n tends to infinity, therefore 1 by a n tends to 0. But it does not imply that this series is convergent. So you have two cases. So the first case is that you assume that this series is convergent. So in that case, it is easy, because this product will converge then absolutely and uniformly on all comparison set. Hence, this will represent an entire function. So you got an entire function with zeros exactly at ans. So this is a simple thing. So now what happens if 0 is a 0 of order m? So you just need to compute, consider this thing. You multiply it with z power m into this product. So this represents an entire function with 0 at zeros and ans. This is a given required entire function. So you obtain the function with the zeros at exactly at the given points. Now, how does a general form look like? So by note 2, we have already observed that an arbitrary entire function with the above property has the form, has this form. So this is easy to prove. In fact, so suppose fz is an arbitrary entire function with zeros exactly at 0 of order m and at ans. Then what happens? You consider this ratio fz by this. Then what happens? This is an entire function with no zeros, because it's only points are 0 and ans, but those will be the removable singularities. So this you can define it as an entire function which is non-zero. Then what happens? By our first lemma, this you can write as a exponential power gz. So fz will be this into exponential power gz. That's what we get. Okay. So in this case, there is no additional term coming to picture. Now case 2. So this is the situation when we handle when this convergence happens. Now what happens if this need not converge? Then you need to add some quantities, additional quantities, to make this convergent. So my claim is that there exists polynomials Pn set such that this product is convergent. Product 1 minus z by n into this product will converge to an entire function. So whenever I say that this product is convergent, I mean that you take the series with log of this, that converges. So then keep in your mind that I am taking the principal logarithm. So log of this should converge. That's so you should be able to choose Pn in such a way that some series with terms log of this should converge. So let me see what is that. So you denote it by Rn set. Rn set is log of this. That means log 1 minus set by An plus Pn set. So I need series with this term should converge, where I should be able to choose Pn set such that this series with this terms converges, and Rn set is log of this. So imaginary part of Rn set, which should lie between minus pi and pi. That means I should be taking only the principal logarithm, principal branch of the logarithm. So these are the conditions I need. So let me see how it is possible. So what we do, you consider the compact disk mode set less than or equal to R. So there are only finitely many ANs will be there, since AN diverges to infinity. So you consider only terms with mode AN greater than R. Don't take those finitely. You can avoid those finitely many terms. That will not affect the convergence, however. Now you consider log 1 minus z by An. Since mode ANs are greater than R and modes are less than R, so this has a Taylor series expansion, which we know this. Yeah. So this is the Taylor series expansion. Now choose Pn set to be the negative of this to finitely many terms. So you take z by An plus etc. some Mn. So I can choose any Mn for the time being. So now Rn set is log of this plus Pn set, that is only the tail term, because this is an infinite series and this is the negative of that. The sum will be the tail term of this infinite series. So that is the tail term of the series expansion, log 1 minus A. Now what happens, we do some computation, estimation. Mode Rnz is bounded by this quantity because this is the tail term. Now you replace each k by mn plus 1 because k is greater than or equal to mn plus 1. There is a typo here, but k is greater than or equal to mn plus 1. So 1 by k will be less than or equal to 1 by mn plus 1. So you can replace it. So now what is remaining is summation of this series, and you take the mn plus 1 term outside. So this become a geometric series with the term ratio is less than 1. So you can estimate this. I mean, use that and just simply use this. I mean, geometric series has the sum 1 by 1 minus R. So now, yeah, this is easy. Now what happens, mode Rnz is bounded by this quantity, and as n tends to infinity, mn tends to infinity, and this goes to 0. That's the thing. So Rnz tends to 0 as n tends to infinity. That's one thing. Since Rnz tends to 0 as n tends to infinity, for large n, you can choose Rnz such that its imaginary part lying between minus pi and pi. So that problem is sorted out. Now you can easily prove that this series is convergent. So this series is convergent. Therefore, series with nth term Rnz will be convergent by the comparison test. So that's all from the one. So you have summation Rnz converges absolutely and uniformly on mode set less than or equal to R by comparison test. Also, you can choose imaginary part of Rnz lie between minus pi and pi. Therefore, my claim is justified. That means summation log this quantity converges absolutely where you are taking the principal branch of logarithm. It is possible you are able to choose such a Pn set so that this will converge. So that is the first important part of this proof. So therefore, by our result on infinite products, this product is convergent. So for a particular choice of Pn set, this product converges uniformly on all compact subset, and hence it represents an analytic function in the whole complex plane. And this function has zeros exactly at ans, that you can easily see. So what we achieved is that we obtained, say you denote it by f tilde z raised to m into this product. So this represents an analytic function, an entire function with zeros exactly at 0 and at ans. Okay. Now we got such a function. Now the thing is that how the general form look like. Suppose you have an arbitrary entire function with zeros exactly at 0 of order m and at an. Then how does it look like? You consider, similarly, you consider f by f tilde z, this will not have any zero, because the zeros will be the removable singularities here. Zeros of f tilde will be the removable singularities here. So this is a non-zero entire function, and hence by the first result, this will be equal to some exponential gz. Therefore, fz will be look like f tilde z into exponential gz, and that means fz has this representation, and where p and z is this. So let me write the final expression like this. So this is the Weierstrass infinite product theorem. So it's a very remarkable result due to Weierstrass. It characterizes all entire functions. It tells you how does an entire function look like. So that is the beauty of this result. Now let us see some consequence of Weierstrass product theorem. First consequence is that using this result, we are able to characterize all meromorphic function on the whole entire complex plane. We know that a rational function is a typical example for a meromorphic function. A rational function means it's a quotient of two polynomials, and this result tells you that a meromorphic function on the whole complex plane will look like a rational function. I mean, instead of polynomials, you will have an analytic function. So every meromorphic function on the whole complex plane is a quotient of entire functions. So that's what we have. This is easy to prove. Let me leave the proof for you, because you start from a meromorphic function with poles at an, and you construct an entire function with zeros exactly at an, and you consider fz into fz, that is gz, and you can easily see that g is entire and like a non-zero. So you have a fz can be written as gz by fz. Now the next consequence is this. Now you look at the proof again. You can see that we are bothered about the convergence of this product. Okay, so this product converges exactly when this represents since this series converges. We use the convergence of this series. Okay, now here mn depends on n. Now suppose we are able to choose mn independent of n. Suppose there exists an h such that if you replace mn by h, it will work for this convergence happens for all, means it is independent of n. So that means you replace mn by h, then this is independent of n plus 1 n, therefore you can take this h part outside. So the convergence depends only on this part. I mean, summation n equal to 1 to infinity 1 by mod a n power h plus 1. So this product converges exactly when this converges. Okay, so this is the thing. So does there exist an h with this property? That's the question. In fact, that you can easily obtain, because you need to choose h such that this is convergent. Okay, so if h belongs, so now you choose the smallest such h with this property. Okay, so if you choose such an h with this property, then this will converge and represents an entire function. All other computations are the same. Now the smallest such h is called the genus of the sequence A. So once you use that smallest h, this product is called the canonical product. So this h is called the genus of the canonical product, and the term genus has different meanings in several ways. So for example, in topology, it represents the number of holes in a manifold. For example, disk has genus 0, torus has 1, and so on. But here we mean something special. Now another definition of genus for functions I will give you now. Now for example, if you consider 1 by n, you know that summation mod 1 by n is diverges, but summation mod 1 by n power 1 plus 1 is convergent. So 1 is the genus. So that is easy. So now in the general form of entire function with zeros an, you have this. Now again consider this expression. Now what happens? We will always use the canonical product whenever it exists. So that gives you the uniqueness part. That part unique. So now what happens? If this gz in this expression is polynomial, that means here you have a gz. It need not be a polynomial in general, but in some situation if it becomes a polynomial, then what happens? You look at the degree of that polynomial and look at the h here. Okay, so we see whichever is larger. So that is called the genus of this function f set. That's what we. That's how do we define genus. And in fact, I have given examples of genus functions with genus 0, functions with genus 1, and you can characterize all such functions of that form. And we are able to compute genus of certain thing and so on. So now we see certain applications. So let us come back to the motivation from Euler, sin pi set. You know that sin pi set has all the integers to be its zeros. So now this summation 1 by mod an becomes now summation 1 by mod an, m mod n, that diverges, you know, but its square converges. Therefore the genus is 1, h equal to 1. Therefore by our representation sin pi set will be z, m equal to 1 here, e raised to g set into product like this. Only one term will come here because genus is 1. Now we want to compute this gz. So if you are able to compute this gz, you know explicitly how does the product look like. For that, what you do, you know that you consider z minus ez. So there sin pi z is no over 0. So you can consider a principal branch of log sin pi z, and you take the derivative of that. That will lead you to this computation. You will have f dash z by f z. That means f z is for sin pi z. It will give you pi quad pi z. Do the same thing though on the right hand side. You will have 1 by z plus g dash z plus this infinite series. Now what happens? You compare it with the previous representation we obtained. I think I discussed in the I gave it as an assignment. Pi quad pi z is this. So comparing with this, you will have that g dash z is 0. Now a simple computation will tell you that e raised to gz is pi. So sin pi z, you have this representation, pi z into product of this. Now sin pi z by pi z will be product of this again. Yeah. Now what happens? This is an infinite product where you are not taking n equals 0. All other negative terms and positive term will come. So 1 minus z by n and 1 minus z by minus n will come. So that club together will become 1 minus z square by n square. And e raised to z by n and e raised to z by minus n will come. That will become 0. So finally you end up with this formula. Sin pi z by pi z will be this infinite product. Exactly the same formula which was predicted by Euler in 1735. So let me stop here. So the output, means overall summary of this lecture is that we are able to classify all entire functions. That's the thing. So all entire functions are classified. Similarly, all meromorphic function on the half complex plane we are able to classify. I have given certain problems with enough hints. You shall include all these problems in your assignment section. Okay, thank you.